Hello, class. For this video, I want to give you a chance to make sure you're getting everything here just to run through it. So I've done as much of the work for you as I can. So I've shown you the first and second derivative of this function. I've given you a nice big graph of the function. So I want to know on what intervals is this function increasing and decreasing, and on what intervals is this function concave up and concave down. What are the coordinates of the turning points of this function, and what are the coordinates of the inflection points of this function? Okay. I'll let you look at the graph carefully, and then I'll let you go ahead and take a stab at this, and then afterwards you can watch the video and I'll go over this carefully. Okay, I hope you have gone over this. So here's the things I need. I need to know when the derivative is 0, and I need to know when the second derivative is 0. Okay. So the derivative is 0 when? Well, the derivative is 0 when the numerator of this fraction is 0. That's when 2 times 1 minus x squared is 0. Remember, fractions are only 0 when their numerator is 0. So that corresponds to x squared equals 1. That gives me x equals plus or minus 1. Okay, so these are our critical numbers. Those are potential places we could have turning points. Okay. We also need to know when the second derivative is 0. And that's when 4x times x squared minus 3 is 0. And so that's when x is 0, or when x squared is 3, which is to say when x is plus or minus the square root of 3. So I'm going to go ahead and record that information on two number lines. Okay, so namely one number line where I'm going to mark off the first derivative zeros, which were minus 1 and 1, and one number line where I'm going to mark off the second derivative's zeros, which were minus square root of 3, 0, and square root of 3. Okay, and again, just to label clearly what we're doing, these are zeros of the first derivative. These are zeros of f double prime. Okay, and again, the reason why we've done this is because these are the potential spots where our function could change, in this case, tonicity. That is, it could change between increasing and decreasing, or decreasing and increasing. And here are the places it can change concavity, or bendiness. It can change from concave up to concave down, or concave down to concave up. Okay, so let's look at the graph to figure out where these things happen. So looking at f prime first, you can see there it's decreasing to increasing and increasing to decreasing. And so those correspond to our minus 1 and our 1 points. So this looks like decreasing, increasing, decreasing. And so if we were to write this, we could write that the function is decreasing from minus infinity to minus 1, and from 1 out to infinity. And it is increasing from minus 1 to 1. Okay. We'll write down the turning points in a minute. But let's look now at the concavity piece. Okay. So over here, we're looking to the far left. And so what's true about the concavity at the far left? Well, at the far left, the function is concave down. That's here. Okay. So here the function is concave, and I'm going to put a straight down arrow to indicate concave down. Okay, and that transitions to a concave up somewhere around here. Okay, so then it's concave up, which then swaps backward to concave down here at 0, as you can see, and then switches back to being concave up over here. Okay, and so this function, if you want, it is concave up on the interval minus square root of 3 to 0 and square root of 3 to infinity, and it is concave down on the interval minus infinity to minus the square root of 3 and the interval 0 to square root of 3. Apologies, I wrote that off the screen. Okay, so then what remains to do is to write down the turning points and the inflection points. Okay, and so these 5 things, these are the x-coordinates of the turning points up here and the inflection points down here. So my turning points they have x-coordinates minus 1 and 1. My inflection points, they have coordinates minus square root of 3 and 0 and square root of 3 as their x-coordinates. And so to get the y-coordinates, again, we're looking for points on the original graph. So we have to plug them back into the original function. Okay, so this is our turning point at minus 1. I'm going to try and put the circle over each of these things as we calculate it. Now you could guess from the picture that probably it's going to have a y-coordinate of 0. But when you plug it back into the function, you definitely get a y-coordinate of 0, because you get minus 1 plus 1 squared is 0 squared divided by something, and so it is indeed minus 1 comma 0. Okay. When I look at the turning point over here at 1, that's that one, I need to plug in 1 to this, and so I get 1 plus 1 squared, which is 4, divided by 1 squared plus 1, which is 2. So that is to say the y-coordinate here is 2. Okay, so that's the turning points. Okay, now we're going to talk about the inflection points. So this inflection point, somewhere about in here, where it switches between being concave down and concave up. It's a little hard to see exactly where it is, but it's somewhere in here. And so when we plug this in, we're going to get 1 minus the square root of 3 squared over 4, because square root of 3 squared, or minus the square root of 3 squared in this case, is 3 plus 1 is 4. Okay, and that's not going to get too much better in terms of ways of writing it. If you want, you could FOIL it out and write 1 minus the square root of 3 squared. That's 1 minus 2 root 3 plus 3. So that would be 4 minus 2 root 3. Sorry, I wrote that again off the screen. But if you really wanted to simplify this, it would simplify like that. But putting that in the numerator isn't that much nicer than that. I'll just leave it like that. Okay. The 0 point is nicer because the 0, 1, I plug in 0, and I'm just going to get 1 here because I'm going to get 1 squared over 1. Okay. And lastly, when I plug in square root of 3, I'm going to get something very much like what I got before. I'm going to get 1 plus the square root of 3 squared all over 4. Okay, So that is our turning points and our inflection points and our intervals of concave up and intervals of concave down. So make sure you're comfortable figuring out all of that by being given a function. Okay. There's going to be one more video in this series for this week, and in that video we're going to talk again about what things look like from various graphs. And so we've talked a lot about what these things look like in the graph of the function. We'll do that just a tiny bit more, but we're going to be more interested in what these things look like in the graph of the derivative and what they look like in the graph of the second derivative. So we'll talk a bit about that next time. But until next time, be well.